So, imagine for a second that you're standing on an offshore oil rig right in the middle of the North Sea.
Oh, man. Yeah, just freezing cold, completely isolated.
Exactly. And the air around you is thick. You can actually smell that faint, kind of metallic scent of volatile chemicals in the air.
Right. Highly combustible environment.
Yeah, exactly. And you need to verify a schematic for like a high-pressure valve. So you reach into your pocket, you pull out a standard tablet, and you just tap the screen to wake it up.
Which is something we do 100 times a day without thinking.
Right. But deep inside that device, when you tap it, a microscopic electrical arc jumps across the circuit board. Now, in your living room, that invisible spark means absolutely nothing.
Yeah, it's totally harmless on your couch.
But out there, suspended in that combustible atmosphere, that tiny release of thermal energy is, it's the exact ignition source required to trigger a catastrophic explosion.
It's literally a life or death physics problem.
It really is. And that baseline reality is exactly what we are jumping into for today's deep dive. So welcome. We're so glad you're joining us. Our mission today for you listening is to look at how we are taking artificial intelligence out of those, sleek, climate-controlled server farms and dropping it straight into the most hazardous, disconnected industrial environments on Earth.
Yeah, it's a massive shift in how we even think about deploying AI.
It is, and we're unpacking a really fascinating July 24, 2026 press release, along with its accompanying white paper from a company called EON AI Ventures. They are introducing this new framework called Field IQ Edge.
Which is tackling a huge architectural headache, honestly.
Right. Like, how do you bring advanced work intelligence to places where the internet essentially doesn't exist and the air itself could just explode?
Yeah, and the core tension we're exploring today really revolves around that exact clash of environments. Because work intelligence, historically, is this heavily centralized concept.
Like, it needs the cloud.
Exactly.
Yeah.
It refers to enterprise-level AI that relies on, massive data lakes, live telemetry, and just immense cloud computing power to optimize workflows and guide frontline workers.
So it's inherently greedy for bandwidth.
Oh, incredibly greedy. But heavy industry. I mean, we're talking chemical processing plants, subterranean mining, offshore drilling. Those places are actively hostile to bandwidth.
Right, because of all the concrete and steel.
Yeah, the physical materials degrade the signal. Or, in a lot of cases, connectivity is intentionally restricted for strict cybersecurity reasons. So what makes EON's Field IQ Edge framework so compelling is that it finally stops trying to force a cloud-centric model into environments that physically reject it.
Okay, let's unpack this, because before we can even touch on like neural networks or edge computing algorithms, we actually have to deal with thermodynamics.
Yes, the physical hardware reality.
Right, because the white paper highlights this phrase that I think frames the entire challenge. It says, software is not intrinsically safe.
That's a great quote.
It is. But, my immediate thought, and probably the thought for anyone who uses consumer tech, is just, armor it. Right.
Just put a big case on it.
Yeah. It's like trying to use a delicate smartphone while deep sea diving, but instead of water pressure, the risk is a literal explosion from a tiny spark. So why does the software care about the dust or the gas? Can't you just encapsulate the battery and the motherboard in some thick, inert resin, slap a military-grade rubber shell on it, and send it out to the refinery?
I mean, logically that makes sense, but practically, encapsulating a computing device in resin just traps the heat, and unmanaged heat destroys processors very quickly.
Oh, right. It would just melt itself.
Exactly. But more importantly, a rugged case, no matter how thick it is, does absolutely nothing to alter the fundamental electrical properties of the device inside.
Because the software doesn't make the spark.
Right. The software code processing an image doesn't cause explosions. The hardware executing that code does. So when the industry talks about a device being intrinsically safe, they aren't talking about drop protection. They're talking about highly specific engineering standards that govern the actual physical energy limits of the hardware.
Like the certifications mentioned in the paper, ATEX and IESEX.
Yes, exactly.
Yeah.
Global certifications like ATEX in Europe and IESEX internationally, they dictate the maximum surface temperatures and the precise electrical energy storage limits of the device.
So it's about finding that minimum ignition energy, like the exact amount of joules required to ignite the specific gas or dust in that specific work zone.
Precisely. I mean, hydrogen requires significantly less energy to ignite than, say, propane. So the hardware must be engineered in such a way that even if it's dropped, crushed, or if it internally shorts out, its capacitance and inductance physically cannot release enough thermal or electrical energy to reach that minimum ignition energy threshold.
Wow. So even if it completely breaks, it just doesn't have the juice to cause a spark big enough to matter.
Right. And historically, because of that strict limitation, computing in hazardous zones was just primitive.
Yeah.
Intrinsically safe devices were stripped down to their absolute barest components. No advanced processing, no AI.
Just really basic digital clipboards, basically.
Exactly. But what EON AI Ventures is highlighting here is this recent inflection point in the hardware market. We finally have 5G smartphones, 10-inch tablets, and hands-free wearables that can process massive data locally, but they still carry those manufacturer-declared ATEX or ISEC certifications.
And the paper was very clear with the disclaimer, right? EON doesn't actually manufacture this hardware.
Right, they're a software and framework company. But the existence of these modern certified devices is what provides the physical canvas required to actually run edge AI in a blast zone safely.
Okay, so we've got the thermodynamics handled. The tala is not going to blow up the chemical plant.
Always a good start.
Always a plus. But a safe tablet is just a really expensive brick if it can't actually process anything, right? Like you walk down into a concrete sublevel of this plant. You have 0 bars of Wi-Fi. You are totally severed from the enterprise cloud. How does an AI model actually function on a disconnected piece of glass?
That's the real puzzle.
Right. And EON's answer to this is something they call the mission intelligence package. Here's where it gets really interesting, I think, because it's kind of like packing a highly specific survival kit for a 12-hour hike, rather than trying to, drag your entire house up the mountain with you.
That survival kit analogy is actually perfect for visualizing this architecture because you physically cannot download an entire enterprise data lake to a local mobile device. It's too big.
Yeah, petabytes of data.
Exactly. So the mission intelligence package acts as the strictly bounded, highly optimized offline payload. The system analyzes the specific work order assigned to a technician. It compiles only the intelligence required for that exact mission, cryptographically signs it for security.
Oh, wow, so it's fully verified.
Right. And then it pushes it to the intrinsically safe device, while the device is still connected to the secure network in the office.
So looking at the white paper, it lists the payload contents. It's got equipment recognition models, optical character recognition or OCR-approved local procedures, and a subset of the digital twin.
Yes. And that last part is crucial.
Yeah, I want to drill into that, actually, because a digital twin is usually defined as this real-time, massively complex 3D simulation of an entire facility. How do you fit that in a survival kit?
You don't. You extract only the geometry and the metadata relevant to the specific physical assets tied to that exact work order.
Oh, I see.
So if the technician is assigned to service, say, a high-pressure compressor, the mission intelligence package only contains the schematics, historical maintenance logs, and spatial data for that specific compressor and its immediate surrounding infrastructure.
Okay, that makes total sense. And the framework maps this out as one experience across 3 connectivity states: connected, degraded, and offline.
Right. The worker starts connected in the office, moves to a degraded state out in the yard where a local edge server might give them partial data, and finally hits that true offline state deep behind the concrete.
But wait, let me push back here for a second.
Mm.
If I'm that technician in the offline state, right, and I get halfway through repairing that compressor, what happens if I uncover a sheared bolt or, I don't know, a corroded secondary valve that wasn't in my assigned procedure? My survival kit doesn't have the schematic for it, and I can't just ask the cloud.
And that happens all the time in the real world. What's fascinating here is how the architecture handles that reality through a mechanism they call evidence capture and governed synchronization.
Okay, what does that actually look like?
Well, the system clearly exposes its offline limits to the user. It doesn't pretend to have an answer it doesn't possess. Instead, it allows the worker to continue any approved local tasks while utilizing the device to meticulously document the unexpected anomaly.
So they just take a picture of it.
Basically, the worker captures a high-resolution image of that corroded valve. The Edge software instantly runs local OCR to read the serial number off the rusty tag, and then it cryptographically signs that capture with a timestamp, the device ID, and the worker's biometric ID.
Ah, so it creates an immutable hash of the evidence right there on the device.
Exactly. It locks it in.
But what happens, say, an hour later, when this worker and maybe 3 other technicians who are also offline logging conflicting data about adjacent systems all walk back up the stairs and suddenly hit the Wi-Fi range simultaneously?
Yeah, you'd think it would just be chaos, right?
Totally.
But the system uses a state-based synchronization ledger. When connectivity is restored, the device doesn't just blindly overwrite the master enterprise database.
Oh, thank goodness.
Right. It uploads those cryptographically signed hashes. The enterprise layer then evaluates the precise sequence of events based on the timestamps in the equipment state at the exact moment of capture.
So it pieces the timeline back together.
Exactly. And if there is a conflict, say two workers log different statuses for the same overarching system, the governed synchronization protocol flags the discrepancy for a human supervisor rather than forcing some automated resolution. So work continues locally, but the knowledge is reconciled globally with strict cryptographic integrity.
Which keeps the data pipeline clean and safe. Okay, so we're talking about taking this hyper-specific AI package offline, but that inherently brings up the hallucination problem, doesn't it?
It absolutely does. It's the elephant in the room.
Right, because we all know that generative AI, when it faces an information gap, has this terrible habit of just confidently inventing answers. Dan Lajerskar, the chairman of EON, stated this directly in the press release. He said, quote, "Our objective is to carry the smallest verified package that can safely support the assigned mission, not to place an unconstrained chatbot in front of critical equipment."
Yeah, an unconstrained chatbot is the exact nightmare scenario for an industrial safety auditor. I mean, a hallucinated fact in a marketing email is embarrassing.
Right.
A hallucinated torque specification on a volatile chemical pipeline. That is lethal.
Yeah, that's a whole different stakes game.
Exactly. To neutralize this threat, EON engineered the Field IQ Edge framework around rigid trust boundaries. They explicitly sever the architecture into two distinct layers: generative assistance and execution authority.
Okay, so what does this all mean? Let me play devil's advocate here. Isn't the whole selling point of generative AI that it can figure things out on the fly? By shackling it with these deterministic safety gates, aren't we kind of defeating the purpose of the AI? It feels like hiring a genius navigator for a road trip, but then locking the steering wheel so they can't actually drive the car.
I get that analogy, but you have to understand the environment. In these hazardous zones, guessing leads to disaster. The cognitive processing power of the generative model is invaluable for interpreting unstructured reality, but it simply cannot be trusted with operational control.
So what does the generative assistance layer actually do then?
It's the layer that looks through the device's camera, parses the rust covering a serial number, recognizes the specific model of a pump, and instantly retrieves the correct 500-page safety manual.
Okay, wow.
Yeah. It can summarize the lockout-tagout procedure in seconds. That is highly complex cognitive work. But the execution authority, the system that actually dictates the sequence of steps, manages permissions, and confirms a task is complete, that operates entirely on deterministic services.
Deterministic meaning that a specific input will yield the exact same output 100% of the time, without variance, no AI guesswork.
Correct. The deterministic state machine sits as a physical gate between the generative model's output and the user interface. It acts as the ultimate authority.
So how do those two layers actually interact technically out in the field? Let's go back to that corroded pipe. Say the generative AI analyzes the corroded pipe and suggests, I don't know, just cutting it with a torch to save time because it scrapes some generic repair forum in its training data.
Right, a classic hallucination. The deterministic layer takes that generated suggestion and parses it against the cryptographically find, engineering-approved procedure that was loaded in the mission intelligence package.
Okay.
Since cut the pipe with a torch is obviously not a valid authorized state transition for that specific offline workflow, the deterministic layer simply blocks the generative output from reaching the worker.
It just intercepts it.
Yes. And more importantly, it triggers a hard stop condition. The system dictates that the workflow cannot proceed, and it mandates an escalation to a human supervisor. It clarifies, it stops, or it escalates. It physically cannot guess.
It stops rather than guesses. That is just a profound divergence from how Silicon Valley typically builds AI software, isn't it? Like, usually friction is viewed as a bug to be smoothed over as fast as possible.
Exactly. But here, friction is the primary safety feature.
Wow. Okay, so moving from this theoretical architecture to the actual deployment. The white paper, which is titled "When the Network Ends, Work Continues," lays out a very specific roadmap for getting this into a facility. They outline this 90-day pilot framework focusing on one bounded work area, one exact device configuration, and a really limited set of assets.
Yes, it's very constrained.
But, I mean, in a tech landscape where massive software updates are pushed globally in an afternoon, spending 3 entire months just to test one bounded area on one tablet model, That feels intensely slow. Why not scale it immediately if the tech works?
If we connect this to the bigger picture of heavy industry, you have to realize that caution is speed. Moving fast and breaking things is a catastrophic philosophy for an oil refinery.
Right, because breaking things means explosions.
Exactly. This rigorous, measured approach reflects EON AI Ventures' institutional DNA. They aren't some newly minted software startup trying to disrupt things overnight. They are the architects behind the broader work intelligence platform tools like Genesis, Field IQ, and Assess IQ.
So they've been around the block.
They've been building on a 25-year foundation of deploying immersive learning and spatial computing technology in over 80 countries. So they understand deeply that digital transformation dies instantly on the factory floor if the frontline workers do not implicitly trust the tool.
That makes sense. But how do you mathematically prove that trust within that 90-day window? Like you mentioned identity verification earlier. If I'm offline in a basement and I hand my tablet to another technician to complete a step, how does the system even know who has the device if it can't ping an enterprise authentication server?
That is exactly the kind of thing the pilot tests. Offline identity verification requires localized biometric processing. So, like an iris scan or a fingerprint matched against an encrypted, locally cached credential token that has a hard expiration timer.
Oh, so it checks against a temporary ID stored on the device itself.
Right. The edge device processes the authentication without ever calling the cloud. And the pilot also ruthlessly tests edge processing latency.
Because if a worker is holding a heavy tool in one hand and waiting 10 seconds for the AI to recognize a valve on the screen,
They're just going to put the tablet away.
yeah, they'll bypass the system entirely.
Exactly. Edge processing must be sub-second to maintain operational compliance. But the most critical element the pilot validates is this concept of safe fallback. If the intrinsically safe tablet is dropped and the screen shatters, or if the edge software encounters a fatal error, how does the system fail? Does it fail open or does it fail closed?
Meaning, does the digital lock on a piece of machinery stay securely locked, or does it spring open when the tablet dies?
Right. The 90-day pilot is designed to prove that evidence integrity holds up under extreme environmental stress, that local latency doesn't introduce hazardous delays, and that those deterministic stop conditions fire flawlessly every single time the system attempts to operate outside its trust boundaries.
So proving it small is the only way to prove it at all.
Proving that in one bounded area, on one specific piece of hardware, is the absolute prerequisite for scaling it to an entire industrial plant.
So, synthesizing all of this for you listening, what we are really observing today is the engineering of a highly specialized explosion-proof bridge. EON AI Ventures Field IQ Edge is taking the immense cognitive power of cloud-based work intelligence, stripping away the lethal danger of the unconstrained chatbot, packing it into a cryptographically secure offline payload, and safely deploying it onto the grittiest, most hazardous job sites on Earth.
It's a massive technical achievement.
It really is. And whether you are managing an offshore rig or just, utilizing AI to streamline your inbox, understanding how we force artificial intelligence to safely interact with the physical world bound by strict deterministic rules is critical. Because this transition from cloud theory to physical consequence, that is the next great technological frontier.
It is the frontier, absolutely. And it fundamentally redefines our relationship with automated intelligence, which actually raises an important question as the final thought I want to leave you with today, building directly on this concept of trust boundaries.
Oh, okay. Let's hear it.
In heavy industry, as we just discussed, we are intentionally designing AI systems where the algorithm is explicitly banned from being the ultimate authority. We demand mathematically rigorous deterministic stop conditions to prevent an AI from guessing when human lives and physical infrastructure are on the line.
Right. The friction is the safety feature.
Exactly. But as generative models become increasingly integrated into the fabric of our daily existence, how long until we are forced to apply this exact same trust boundary framework to the AI managing our digital lives?
Oh, wow.
When our personal algorithms, the systems curating our information diets, executing our financial trades, and filtering our communications, inevitably lose connection to our active human oversight, who is coding the deterministic stop conditions for the unconstrained chatbots running quietly in the background of our society.
Man, when does the digital AI need a hard stop condition? That is a phenomenal question to chew on as these systems grow more autonomous by the day. Well, thank you so much for joining us on this deep dive. Keep questioning the technology around you, keep exploring those boundaries, and we will catch you next time.